Hi everybody. Today we're going to start with a review of the periodic table, some relevant information here, and then we're going to change gears to a POJOL packet on naming ionic compounds. To start with some review of the periodic table, remember metals are on the left of the periodic table and nonmetals are on the right of the periodic table. It's all relative to the metalloid stair-step line, which we have highlighted in blue here. So you can see there are about 7 metalloids on the periodic table. And to the left, we have the metals, and to the right, we have the nonmetals. So you can see that the vast majority of elements on the periodic table are metals. The only exception on the periodic table is hydrogen. It's located on the left of the periodic table, but it's a nonmetal. So again, you can see we have the metalloids highlighted in blue. And in our POJOL packet on naming ionic compounds, I also highlighted the metalloid stair-step line blue. So the POJOL packet in Model 1, it gave us information about cations and anions, but mixing in the review that we just did, we know that metals are to the left of the metalloid stair-step line. So this supports the concept that metals like to lose electrons to take positive charges, becoming cations, and conversely, nonmetals like to gain electrons, taking negative charges, and we call those anions. So cations have positive charges and anions have negative charges. The other day in class, we also learned to describe ionic compounds as those that mix together a metal with a nonmetal. So again, if you take a look at the elements that are in the compound, like sodium chloride right here, sodium is a metal on the left of the periodic table. Chlorine is a nonmetal on the right of the periodic table. When you have a metal bonded with a nonmetal, that's called an ionic compound. We also described 3 rules about ionic compounds. Rule number 1 is most important. Remember, they have to be electrically balanced. Whether you want to think of it in these terms up here, or I've got it color-coded in the same highlighter color at the bottom, it means the same thing. So the end of the question 2 and 3 says, keep in mind that the sum of the charges in an ionic compound must equal 0. So for example, if we want to mix together potassium ion and sulfide ion, we know that potassium has a +1 charge, and we know that sulfide ion has a -2 charge. And what I told you in class was that once we have the correct species written down, the formula and charge, all we can do is to copy and paste the correct species so that the sum of the charges equals 0. So we would need to copy and paste 1 more potassium ion. Now +1 + 1 -2 does equal 0. Another way that you can represent this with what I call a balanced charge teeter-totter is 2 K1 pluses, potassium ions, 1 single sulfide ion. Because there are 2 potassium ions, whether you look at it this way or this way, the formula is K2S. I also have similar information down here about the 2 forms of iron sulfide. Remember, iron is one of those unusual elements on the periodic table that like to take different charges. Iron likes to take either a +2 charge or a +3 charge. So if iron is in the +2 state, there is a 1-to-1 ratio Fe2+ to S2-. So that form of iron sulfide would be FeS. But if it's +3, iron in the +3 state, you can see that the least common multiple between 3 and 2 is 6. You find the least common multiple by multiplying the 2 charges together. So we would need 1 extra iron ion in the +3 state, and we would need 2 extra for a total of 3 sulfide ions. For that reason, it's Fe2, and then S3 would be the correct formula for this form of iron sulfide. Okay, that's a little review of some stuff that we did last week in class. Now I want to flip the page over, and remember, in these types of packets, which are called POJOL packets, you're going to take a look at some information in a model. This is Model 2 right here. Read and study the information right here, and then you're going to answer questions. If you're not sure about the answer to the question the second that you read the question, that's perfectly fine. Use it as a prompt to go back and reanalyze Model 2, and figure out what the answer to that question is. Okay, learning how to read formulas and how to read names. I'm going to read these off to you. This would be NaCl, which is sodium chloride, CaS, which is calcium sulfide, Ag2S, which is silver sulfide. Notice we just say the number 2 right here. So this is Ag2S, silver sulfide. Using that same convention, we would say Zn3P2, which is zinc phosphide. Al2O3, which is aluminum oxide. And this one says SrCl3, which is strontium chloride. But I want to point out that there's actually a problem with this one right here. This one right here says that the ratio is 1 strontium to 3 chloride ions. But if we take a look at our periodic table, we can see that when strontium turns into strontium ion, it takes a +2 charge, and when chlorine turns into chloride ion, it takes a -1 charge. So if I make a balanced charge teeter-totter out of this, it would be Sr2+, Cl1-. And again, once we have the correct species, there are formula and charges up here in standard format, all you can do is to copy and paste the work that you've done. So you can see that the least common multiple between 2 and 1 is 2, so we need to have 1 extra chloride ion over there. For this reason, the correct formula for strontium chloride is SrCl2. So there was an issue with that. Okay, one last thing that I want to remind you of before you get to work on questions 4 through 15 is that sometimes you're asked to think about these unusual transition metals that are right here. Just remember, silver always takes a +1 charge, cadmium always takes a +2 charge, and zinc always takes a +2 charge as well. All right, thanks a lot, guys, and see you soon.